So now we're going to look at more integrals of trig. Let's talk about the ones that we already know. Okay, so up to this point, we already know 6 trig integrals. We know that the integral of the sine of x is the negative cosine of x because the derivative of cosine of x is negative sine of x. Similarly, we know the integral of cosine of x with respect to x is sine of x. Of course, plus c in all of these because the derivative of sine of x is cosine of x. And then I think to myself, well, what are the other functions that I know their derivatives? I know the derivative of tangent. Its derivative is secant squared x. Therefore, I know the antiderivative of secant squared x is tangent of x. Which other ones do I know? I know cotangent. Well, cotangent has a negative derivative. Therefore, if I write it positively, then the antiderivative will have to be negative. Negative on one of those sides, right? So the antiderivative of cosecant squared x is negative cotangent x. What are the other ones we know? Secant and cosecant. Secant's derivative is secant x tangent x. Therefore, the antiderivative of secant x tangent x is secant x plus c. And I also know the antiderivative of cosecant x cotangent x with respect to x. It's negative of cosecant x plus c. So we already know these. But we don't know, if I asked you the antiderivative of tangent, it's not on our list. The antiderivative of cotangent is not on our list. The antiderivative of secant is not on our list, and the antiderivative of cosecant is not on our list. So 4 more that we want. The antiderivative of tangent, the antiderivative of cotangent, the antiderivative of secant, and the antiderivative of cosecant. So before I just give these to you, let's take a look at what is tangent of x without using the formulas. So I'm not going to give you the formulas yet. Let's do the antiderivative of tangent of x. Well, what is tangent? What is tangent of x? Tangent can be rewritten as sine x over cosine x. Okay, what does that mean for us? Well, we just talked about using the natural log function for rational functions. This is a rational function. How did we deal with rational functions? Well, we identified that the denominator should be our u because we're looking for u prime over u, and we wrote that u is that denominator, so therefore what is the derivative? Du dx. In this case it is negative sine of x. Solve for dx, so dx is du over negative sine of x, and we substituted it in there. So let's rewrite. We have the integral of the sine of x, over u. Dx became du over the negative sine of x. So the sine x functions cancel out. I do have this negative, but I can bring it out. So this is the negative of the integral of 1 over u du. Well, that's the negative of the natural log of the absolute value of u plus c, or with u plugged in, the negative of the natural log of cosine of x plus c. So this is pretty easy, but a pretty long way to go from the antiderivative of tangent of x to negative natural log of absolute value of cosine of x with all this rewriting, use substitution. Instead, let's just memorize them. We memorized these first 6. We can memorize 4 more. Not a big deal. So let's do it. The antiderivative of the tangent of x is the negative natural log of the absolute value of the cosine of x. Of course, all of these plus c. The antiderivative of cotangent of x, the natural log of the absolute value of the sine of x, plus c. Antiderivative of secant x, the natural log of the absolute value of secant x plus tangent of x, plus c. And the antiderivative of cosecant x, natural log, oops, left out the negative. This one's negative. The negative of the natural log of the absolute value of cosecant x plus cotangent x, oh, plus c. So notice some similarities between derivatives and integrals. The derivative of the secant is secant times tangent. In the antiderivative of secant, secant plus tangent, but natural log in there too. So natural log in there. So these make sure that you memorize. That'll be so much easier than having to recreate these formulas. So I can show you where this antiderivative of secant x comes from, and it's quite interesting. It's not necessarily something that you just think of off the bat, but it's easier really if you just memorize it. So we memorize the integral of secant of x, and we know it's just the natural log of the secant x plus the tangent x plus c. If you're interested in seeing why, keep watching from here. Otherwise, fast forward to the next two problems. Don't skip over the next two problems because I want to show you how to use them. In fact, let's talk about how to use them now, and I'll come back and do the next one. So in number 3, evaluating the following integrals. So I'm not going to think about the fact that it's rational function. I'm going to think about the fact that I have secant in here. And I know that the antiderivative, I'm looking at my list, or I've memorized it, the natural log of, the integral of secant of u with respect to u is the natural log of the absolute value of secant u plus tangent u plus c. So I'm thinking this, therefore I want this to be my u. So I'm going to be doing some u substitution. So u is the square root of x, and I know du dx is 1 over 2 square root of x. Solve for dx, and I get 2 square root of x times du. Do a substitution in here. Integral of secant of u over, so my denominator is still 5 square root of x, dx is 2 square root of x du, and then I've got square root of x with square root of x. Square root of x over square root of x, gone. 2/5. I can pull those out. So what does this look like? 2/5 integral of secant of u du, and I've already memorized the integral of secant of u du. So now I just put it in there. Natural log of the absolute value of secant of u plus the tangent of u plus c. Don't forget to substitute what u is. So natural log of the absolute value of secant of square root of x plus tangent of square root of x plus c. Yay. Number 4, why don't you try it on your own? Pause the video, come back, see if you got it. So what's in the tangent function? I'm going to call it my u, and du, this time with respect to t, 2. dt is du over 2. Plug it in there, du over 2. So rewrite my integral. Tangent of u times du over 2. Well, the over 2 is a little bit of a bother, but it's just a constant multiple. It can come out. Only numbers can come out, not variables. So 1/2, the antiderivative of tangent of u is the negative natural log of absolute value of cosine of u plus c. Pull out the negative, negative 1/2 natural log of the absolute value of cosine of 2t plus c. Now here's some things that are tricky that you need to be aware of. Remember all the ways that we said that we could rewrite this? So this is a good answer. But what else could you possibly see? Sure, you could bring the half as an exponent, or just the negative as an exponent. In fact, perhaps you bring the -1 as an exponent. Well, what is cosine to the -1? What's the cosine function flipped over? The reciprocal of the cosine function? That's right, the secant function. So this could say the natural log of the absolute value of the secant of 2t plus c. That's a good answer. and quite tricky that it looks like a different function, but it's just the reciprocal function because of the negative. Be careful with that. So perhaps we could even take the 1/2 and rewrite that with the square root. We don't really need the absolute value anymore because we know we can't take the square root of negative numbers. So now this is a good answer. Be really careful with your natural log functions and all the different ways you could see the answer. So now if you're interested, I'm going to go back and show the proof for number 2, why the integral of secant of x is what it is. Please hang around if you're interested. So here we are in number 2, and I'm probably going to give myself a clean page for this. So here is what we're starting with, the integral of secant of x dx. And I am thinking about where I'm headed, and I'm multiplying secant x by secant x plus tangent x over secant x plus tangent x. I can multiply by anything I want as long as I do it in the top and the bottom. So why did I do this? Well, let's see what happens when we multiply by secant x plus tangent x. If I distribute the secant x in the numerator to those parts, I get secant squared x plus secant x tangent x in the numerator. In the denominator, secant x plus tangent x dx. So now you might start to see why I did this. I have a rational function such that if I take the denominator to be my u, what's its derivative? Well, secant's derivative is secant x tangent x. Tangent's derivative is secant squared x. Aha! So we're always thinking of where we're going when we're doing things like this. So I say u is secant x plus tangent x. I say du dx. The derivative of secant x is secant x times tangent x. The derivative of tangent x is secant squared x. And there I see it. I've got it in my numerator. So I can do my substitution and say that dx is du over secant x tangent x plus secant squared x. Let's rewrite. Integral all that guy up there, secant squared x plus secant x tangent x over, we said this is u. Instead of dx, we'll put what dx equals, du over secant x tangent x plus secant squared x. I'm using this. What do we see? The secant tangents cancel the secant tangents down there, all that expression. So what's left? Integral of 1 over u du. We know how to deal with this. Natural log of the absolute value of u plus c, or better yet, the natural log of what u equals. Secant x plus tangent x plus c. Yay.